So basically the challenge with energy storage is just the cost of it. I mean, the compressed air energy storage product in general has been around for a long time. Been running in the United States since I think 1990. But it's not this flexible, easy to site piece of equipment. It's kind of a big old clunky thing. So the challenge is how to make it siteable where, you know, I was just on a phone call with a utility in California. Where can I put this thing? How big is it? You know, because there's this conception of compressed air energy storage is this enormous thing. And just to put it in perspective, I understand where it's coming from because the one that's running in the United States has a storage cavern that's made in a salt dome under the ground, and the salt dome is about the size of the Empire State Building. So it's pretty big. Our stuff comes in 40-foot containers and you stack them. It's in a box, it's very efficient. So the challenge with the efficiency at the power plants is, like we were talking, that they have to turn off and on, and they're going out of business. So what we do is we offer them, like I said, the stepwise piece to get into reducing the carbon by, instead of the power plant compressing the air and then burning it in a turbine, we provide the compressed air from a renewable resource. And when you do that in a gas turbine, basically about half the power that the turbine makes comes out as compressing the air that it took in the first place to make that power. But the key is that our system is, you know, I mentioned a gas turbine is about 35% efficient nominally. Well, if you eliminate the compression cycle, it's 70%. So our system is 70%. Turns out it's between 70 and 80%. And if you look at this modern combined cycle power plant, the best they've been able to achieve is around 60%. And the most common ones are more like 55, and they're being operated at 45 because of this issue of flexibility. So here we come in at 70 to 80 because we're storing the air and compressing it using a renewable resource. And we don't have that bottoming cycle, that steam cycle. And there's a big challenge with that from a water consumption standpoint in a lot of areas, California specifically. So we eliminate, there's no water requirement for ours. Ours is literally just the gas turbine. But because we eliminated that compression cycle, it's at 70 to 80% efficient. And what's important about that is, you know, we haven't talked about the last step of how do you get to carbon free? Because we're still talking about burning natural gas in a regular gas turbine. And all over the world, there's probably hundreds of companies working on synthesizing hydrogen, burning hydrogen in a gas turbine. Matter of fact, I just got off the phone with the same guys talking about their vision, and they're doing a 200 kilowatt demonstration. So 200 kilowatts wouldn't power the floor on this building. It's small. So the last step of our process is, when that technology is ready, these gas turbines that are on the planet today, they will take out the section of the gas turbine that burns the natural gas, and they'll put in a section that burns hydrogen. And hopefully it does it for longer than 10 minutes because they have the hydrogen supply and storage figured out. So since we're using that exact same turbine, when that technology comes along, we just plug it in. So, but the unique thing is, because we're 70% efficient, 70 to 80% efficient, we use 25 or 30% less than the most modern combined cycle power plant, because we eliminated that compression cycle in the overall gas turbine operation. So we'll burn 30% less fuel to make the same power output compared to a modern combined cycle power plant, which consumes some water. So we'll be water-free and carbon-free with hydrogen, burning 30% less fuel than the most modern power plant in the world. And, you know, we enjoy in the United States really low natural gas prices because of the shale gas that happened 20 or so years ago. And, you know, our natural gas prices, although we did just have a recent blip up to $5 or so, that would be still really low in a lot of countries around the world. You know, $5, $6, $7, $8 is common per million BTUs. But like I said, there's a lot of smart people in the world that are working on it, and I'm sure it'll come. It's just when and how much it's going to cost. So, but like I said, with our product, whatever it costs, we're going to burn 30% less of it. So we're going to make it more feasible to have it at a reasonable price in the market earlier. It's kind of like solar panels. Solar energy, I can't quote you the numbers, but it's probably come down by, you know, 20 or 30 times the cost in the last 20 years. So it's becoming inexpensive. And that actually kind of feeds into our product in a way because, and I'll just give you an example. Here in Florida, Florida Power and Light, their headquarters is in Juno Beach, which is like, you know, 5 miles from my house. They're putting in massive quantities of solar plants in Florida. They're actually the largest landowner in Florida, which was an interesting fact I learned recently. And it's because you need a lot of land for solar. And the rule, and I don't know all the regulations, but they build their plants at 74.99 megawatts rated output. Because if they go over 75 megawatts, it goes into a different category, which is different permitting and something or other. So they're 74.99. So how many megawatts you think that solar plant puts out when the sun is right up above it on the perfect day? 74.99? No, puts out about 110. And they do that because economically, when they're going through all the development of the land, purchasing of the land, the infrastructure, all the drainage requirements for the property, actually installing all the solar panels and everything, economically, it works out best to overbuild by about 40% because as some solar panels die off over time, and we have clouds in Florida, right? You don't always get all the perfect sunny days. They're gonna put out 74.99 a lot more time if they have a 110 megawatt rated system. But what do you think they do with the other 40 or so megawatts when the sun's shining bright? They waste it. It goes away. So, for example, in Korea, they have a wind farm that's maybe I think it's a 25 megawatt rated wind farm, and they don't run it at all because I think they did something wrong when they were siting it, and they didn't realize how much fluctuation they would get in the wind. So where it's located on the grid and the proximity to other substations and so forth, they can't actually take the wind and put it on the grid. It causes too much volatility. So they're looking at how to solve that. And our solution is we go to the wind farm and we build a small gas turbine that has our energy storage device on it. And basically when the wind's blowing, we can make power at 75-80% efficiency, and we can store some too. So if they can use it when the wind's not blowing to balance out the peaks and valleys. So there's just this fluctuation in renewable energy and being able to use it.